Okay, so in my previous lecture, I concluded that there was a conflict between several postulates, and so today's lecture is talking in more detail about theories that would relax one or the other postulates. And so the postulates were purity, effective field theory, and no drama. And there were, as I discussed, two kinds of drama, each of which deserves to be discussed: fiery drama and quantum drama. Now, before I start going through this, I wanted to just mention one point about the thought experiment that led to the conclusion that these are inconsistent. Earlier, I talked about black hole complementarity and a thought experiment that was originally used to test it, where you have a bit entangled with another bit that you throw into the black hole. A copy of the interior bit has to appear in order for the information to get out, and these are on the same time slice. But if this appears late enough, no observer can see both. Actually, the current paradox is very similar but different in an important respect, because we have the bit inside, we have the bit outside, but now the illegally entangled bits are the early radiation. And so here you can arrange that no single observer can see both of these, the cloned bits. But here, again, this bit is entangled with both of these, so this bit is sort of cloned in here. And now there's a single observer can see both. And so the problem is that observer has no consistent quantum mechanical story. Also, I don't know if I emphasize this, but Juan mentioned it. In order to make the paradox sharper, it's useful to imagine carrying out a quantum computation on this early radiation. So the B being entangled with these things, with the early photons, is okay. If that's true, then by a quantum computation, you can extract from this a single bit. I'll call it E, then that single bit. So no single Hawking photon is strongly entangled with the later Hawking photon, but some quantum bit that can be extracted from their state is entangled. And so we have these three bits, E, B, and B hat. Okay, so that's just prologue. Now, yes?
How important is this extra bit? I mean, suppose we do not.
Okay, suppose we, that's actually, let me try to answer that in stages as we go along, and you can ask again. Because, yeah. But that will sort of be down here at the level of quantum drama, so I'll come back to that relatively late. Purity, the fact that the information escapes with the Hawking radiation, as I discussed, there are many reasons, including ADS-CFT, for believing that. And I can't say that since this paradox has emerged, any really interesting new ideas for violating purity have come out. People have repeated some of the old arguments in favor of information loss or remnants, but I don't have much to say here. So the second assumption is the assumption that nothing unusual happens outside the black hole. And so what I do is I want to give you one model of how this might be violated. So here's our page curve, the descending entropy in the latter half of the life of the black hole. And what the Hawking process wants to do is it wants to sort of increase the entanglement between the inside and the outside. Suppose, and by the way, this class of models has been most studied by Steve Giddings. He's pretty much, well, he's been the one systematically pursuing it. Suppose in addition to the Hawking radiation, there were some other process that emitted additional radiation in such a way that it carried away enough information to kind of keep us, so these are happening actually to keep us on the page curve. Now, okay, lots of things to say about this. First of all, it's a big effect, but again, any effect that you need to violate, Mythos Paradox. If we think about the bit model, the difference between a bit model that gives the Hawking process and the bit model that gets the information out was an order 1 change in what the bits near the horizon were doing. It's an order 1 change, sort of, at least in the behavior of the quantum fields somewhere near the horizon. And so it has to, it's big in some sense. And this, in this version of things, it's big outside the horizon. So these quanta have to appear. And the first thing is obviously the amount of the total amount being radiated is going up. But that also means, remember, thermal equilibrium relates emission to absorption. So this black hole will absorb twice as much light as a normal black hole. Well, it will look from the outside, it will look dramatically different than from what we think a black hole should look like. Of all of the ideas for avoiding the paradox, this is the most interesting for that reason. Almost every other one would be expected not to have dramatic consequences outside, but this one is fun for that reason. I have to say that when we first realized there was this paradox, my assumption was that this was the most natural way to evade it. Because again, we know now, due to ADS-CFT and the holographic principle, that quantum gravity is fundamentally non-local. And so why should the non-locality be hidden behind the horizon? Why doesn't it have effects that are visible further out? The problem again is that those are not small effects. They're dramatic at a level that we think we understand effective field theory. The other thing is that you can defeat, even aside from any other issues of plausibility, you can defeat this. You can defeat this class of models usually. So these photons are a bit they're different from the Hawking photons. They may have different angular momenta. Actually, they have to be very efficient. You see, they have to be very efficient to carry away so much information. So they have to have lower energy on the average than the Hawking photons. So you could imagine putting a half-silvered mirror around the black hole that reflects these photons back in, but lets the Hawking photons mostly out. And then you would lose this. Then you would be back on the bad curve. So these, it's very hard. It's very hard to make a model in which you by letting the non-locality leak out to several times the Schwarzschild radius, you can avoid the paradox. In particular, there are versions which might be less dramatic than this one, but they're still dramatic and they still can be defeated by more clever thought experiments. So that's pretty much all I have to say, I think, about giving up the assumption that the outside observer sees nothing unusual. Okay, now suppose that in fact, I forget how you spell fiery. Is it that way? No, it doesn't look right. So what we have is an argument by contradiction that says there are high energy particles or something. I mean, it might be something worse than a high energy particle. This is the minimum amount of sort of drama one can have. What can we imagine any mechanism that would produce any kind of structure at the horizon where Einstein's theory doesn't allow any? So there's the fuzzball idea, and one way to motivate this. We know of various places in string theory where we have a time-like singularity, or where the naive geometry is a time-like singularity. But in fact, string theory doesn't have this singularity. The singularity gets resolved basically into a shell of branes. The Polchinski-String model is probably the first example of this. But in all the cases where this happens, we kind of understand dynamically why it does. If you study a brane in the presence of singularity, you find that there's a repulsive force, and so in fact you can deduce that this should happen. Now the black hole singularity is quite a bit different because it's a space-like singularity. It's in the future. It it can't resolve itself in a causal way like this. But if you, I haven't talked at all about the singularity because the problem is all at the horizon. But if you take the point of view the singularity is really bad, there has to be some way to resolve it. Maybe it gets resolved some way like this, and because of the causality, it can't be. It might be a tunneling process, whereby some shell of brains appears on the black hole horizon. So this is a scenario due to Mathur, and I've mentioned his name several times because in trying to justify this scenario, he's sharpened the paradox a number of times in the way that I described. But there's not really, there's toy models with lots of supersymmetry which don't really have real horizons, but there's not really a theory here. The closest there is to a theory is saying, well, the amplitude to produce some kind of coherent brain source is really small, something like that, where S is the black hole entropy. But he's imagined there's lots of shapes of brains, and so that's the state of the art in this subject. I think cosmology used to be at that order of accurate. Now it's gotten better. Maybe this subject will get better. But I don't have much to say here. I should say something. There are not going to be a lot of equations. That's probably the only one in today's lecture. Many of the papers I'll mention do have fair numbers of equations, but I want to, there's none so specific that they're worth going through. I more want to survey the sort of the landscape of ideas. Silverstein and collaborators has been looking at something else, and here's my sort of reinterpretation of what she's doing. So here's again the black. If you see a line doing that, it's probably a horizon. If you see a line doing that, it's probably a page curve. So this one's a horizon. I guess I should dash it then, horizon. And now imagine that we have time slices which differ by, so there's the killing symmetry of the geometry. So time slices according to the killing symmetry. And I don't really care what these are nice slices, but I don't care what they do deep inside. I only care about the geometry near the horizon. Now, if I have a quantum field theory, and in the approximation that the geometry is not strongly fluctuating, treat this as a quantum field theory in curved space-time, I can quantize it on these time slices and derive this adiabatic principle that I've repeatedly used, that as long as the rate of change of the frequencies of the modes is small compared to the frequencies themselves, there'll be no significant particle production. And that's true for quantum field theory because, again, there's no large curvatures or time derivatives near the horizon of a large black hole. Now, there is a large non-local invariant. If we consider sort of this slice as compared to this slice, there's a large relative boost between them. This redshift or blue shift that I've referred to a number of times. Now, in local quantum field theory, a large non-local invariant doesn't have any big effect because physics is local. It doesn't lead to anything dramatic. Maybe string theory is different. Strings are extended. Strings are extended, and we don't understand them completely. In particular, if I wanted to derive the adiabatic theorem, I would do what I told you. I would quantize the theory with this time slicing. I don't think we know how to quantize strings with this kind of time slicing. If you think about how you've seen strings quantized, either covariantly or in light cone time, maybe there is something fundamentally less local about strings that would make them subtle, that would make them sensitive to these large non-local invariants. That's an old idea. It's never really been convincingly realized, but this is in some sense what Silverstein is doing. She's considering sort of an infalling body and a later observer and arguing that maybe adiabaticity breaks down. There's another aspect of this which goes back to Susskind a long time ago, which he points out that if you boost a string a lot, it behaves in a more complicated way than a point particle because the boosting slows down its internal constituents. You can see more and more of the internal modes, and so in some sense it gets larger. And no one has ever really turned that heuristic idea into a calculation, but maybe there's something there. So in terms of actual frameworks for identifying a structure at the horizon, these are ideas that are out there. I'll mention a third, which is again has even less sort of, well, it's just more of a slogan. But we keep thinking that space-time is emergent, that it's something that emerges from other variables, and maybe the point is simply that the space behind the horizon doesn't emerge at all. You might even say the basic atoms of space-time are in a different phase behind the horizon. Now, there's no calculation for this, but it's a possible, outcome of. It's a possible way to think about why something might be dramatic at the horizon. Okay. Now there's a question that you might want to ask. This is still in this context of supposing that in fact there is some kind of physical drama at the horizon. Suppose that in fact at the horizon there is some kind of excitation. Why would we expect the Hawking calculation to still be valid? Would we expect it to still be valid? Certainly when I derived it, I used the notion of what an observer would see as they cross the horizon. I referred extensively to modes that cross the horizon, but that was a crutch. Causality says that what happens outside cannot be sensitive to anything behind the horizon. So if there were some strange phase transition just behind the horizon, it would have no effect on the Hawking radiation. And one can say that in a more general and a powerful way. namely, the black hole seems to be a thermal system. And one property of thermal systems, so what that means is, if we put just from that property alone, we can deduce that the density matrix for B is thermal. It doesn't actually depend on the detailed model of the interior that we had. And while I'm on this subject, I wanted to again address another possible misconception. So earlier I addressed the misconception that a black hole can't be in a pure state by pointing out you could collapse, coherent light, or you could collapse coherent light and you could get a black hole in a pure state. There's another misconception that a pure state can't be thermal. And this is because your statistical mechanics textbooks have lied to you. They've made you believe that thermal behavior is always associated with ensembles. But the truth is, well, let me again think of a thought experiment. Suppose I have a sealed vessel containing some matter at absolute zero, and I fire a laser in. So I heat it up, but everything is pure. Everything's in a pure state. The matter will heat. Eventually, it will burn or evaporate. It will wait long enough. It will come to equilibrium in the vessel, and it will be in its behavior will be in every macroscopic sense thermal, even though it's still in a pure state, right? And the point is that if I have a complicated system, a system complicated enough that it's quantum chaotic, then if I look at any simple variable or set of variables, all the rest of the system is playing the role of a heat bath for the systems that I look at, for the variables that I look at. And so they will always look thermal. They will always look as though they're chosen from an ensemble, even though the whole system is pure. And this principle, by the way, is made more formal by something called the Eigenstate thermalization hypothesis. It focuses actually on energy eigenstates, but it's more general than that. And again, it's getting a lot of attention these days in condensed matter physics as well as other areas. And again, it's just this notion that a pure state looks a pure state of a quantum chaotic system looks thermal. So again, having said that, we take our black hole, we take our CFT or our black hole, either dual version, put it in some high energy pure state, and the mode B, the mode that becomes the Hawking photon, will be thermal. So the Hawking calculation is very robust. This is also another reason why, well, actually, let me come to this. I think it's the next, yes, the next subject. So why can't, or can ADS-CFT tell us which of these is realized? So ADS-CFT was very useful in telling us that information is not lost. We didn't even have to solve the strongly coupled gauge theory, which we can't do. But we didn't even have to solve the strongly coupled gauge theory to come to that conclusion. We only had to know that it existed and that it was a quantum field theory. But now, the problem is, even if we could solve the gauge theory, even if we had all of its correlators, all of its states, we don't know what question to ask it to tell us what is happening in the interior of the black hole. One of the things this paradox has done is to reveal the impotence of ADS-CFT in describing the black hole interior. And many people, myself included, have written papers saying, of course it describes the interior. That's what a duality is. Everything is in there. But I described earlier in my lectures how you could construct sort of boundary representatives that would measure, boundary operators that would measure physics happening in the interior. But now if you've got, it involved, again, integrating the field equations. If you've got a singularity there, and you've also got your infalling body, and you try to carry that construction out for a point behind the horizon, the construction fails because the integration outward runs either into the singularity, or if you try to sort of sneak around, it runs into the infalling body. And so the construction fails. And moreover, the construction depended on this assumption that you understood the bulk dynamics to start with. So it's not useful if you don't actually understand the bulk dynamics. So you don't know how to construct these things. And in fact, there very probably is no operator in the conformal field theory that measures the energy momentum tensor or some other variable there. And Mark van Ramsdonk and also Juan gave one reason for believing this. We could consider the two-sided black hole, where what's happening here depends on things that you did in the other conformal field theory. And if there were some, so there cannot be any operator. So if we had some operator that worked for the one-sided black hole, it should also work here, but it can't work here. So we don't know what question to ask the gauge theory to tell us what's happening behind the horizon, and B, there may be no question in our current state of knowledge of string theory. You might think that the difference between a firewall and a smooth interior would be something very dramatic in the field theory, but it's not. Again, that we just, as I just described, pretty much regardless of anything, the gauge theory will look thermal. And you might think that a firewall will be much hotter or something, but it's not, because all of the drama is down at the horizon where the redshift is enormous. So there's no obvious signature in the conformal field theory to say what's happening behind the horizon, even if it's very, very dramatic. Not all states of thermal equilibrium are the same. I mean, they differ in how they approach equilibrium. They can that very much. They can approach it fast, slow. So they differ in how they approach equilibrium, although even here, that's largely determined by the quasi-normal modes, by the physics outside the horizon. There's a basic limitation to ADS-CFT to be aware of. It's extremely powerful. It gives a precise account of anything remember we have the sharp dictionary for, the operators in the CFT, which are dual to the perturbations of the fields near the boundary. We have a sharp dictionary for that. We have that gives us an enormous amount of information. But if there's something which is invisible to the boundary, it gives us no information. It's sort of as though ADS-CFT is covering one. This is probably not a good analogy, but it's sort of as though ADS-CFT is covering one coordinate patch of the bulk, and we don't know how to describe the other coordinate patches or how to patch them together.
Bill?
Question?
The first lecture you said that you defined string theory by ADS-CFT.
I did.
And now you seem to be giving up on the possibility of ADS-CFT of describing an important state in quantum gravity.
I'm saying that our most complete current description of string theory is not complete. That's all. I'm saying there's still work to be done. Yes.
Regarding this conjecture, what you said that it only describes a coordinate patch of
Yes.
ADS. So, but we know this construction by Hamilton, Cabot, and Lipschitz and Lowe. They considered the Poincare patch, and they constructed operators, smearing functions for operators outside the Poincare horizon. Using these antipodal maps.
So we should probably talk about this offline. We should talk offline maybe in more detail what they did, but I claim that they didn't. I claim they did nothing that evades what I've told you. I mean, I think some of their maps involve both sides of the black hole, which in a two-sided black. Actually, I'll come back to the two-sided black hole later. But yeah. So I'm still on fiery drama, and I want to do one more. I want to use ADS-CFT for something. So what I want to do is I want to give you a different derivation of the firewall problem, which is maybe more robust and which uses ADS-CFT. So here's ADS. I want to work with the eternal black hole. As I explained, the problem is still present there because we can entangle it with an outside system. And there's these Hawking modes B, and these modes do have, I'll call them capital B. These modes, these field modes in the bulk do have identifiable operator duals, precursors in the boundary. So what I want to do is, and I've got a bunch of these modes, I want to work with an eigenbasis for the number operator for the Hawking modes. Now, I want to put the CFT in this eigenbasis. Now, you'll remember that for black holes in their ground state, for black holes in their ground state, n sub B is thermal. So turning that around, in an n sub B eigenstate, it's very far from thermal. It's very far from thermal. And so n sub A is very far from the vacuum. The occupation for n sub A is order 1. Or let me work with projection operators. The projection operator, P sub A, is the projection operator onto the A vacuum. So this projection operator is not close to 1. Acting on any of these states, the expectation value of this operator is, let's call it order 1/2. So now if we average over the basis, the average value for this thing, again, it's of order 1/2 or less in every basis state. So the average value is of order 1/2. So that means if you take a random black hole state, so a random linear combination of the high energy CFT states, the states that look like black holes, the average state will have a 50-50 chance, say, for this particular mode to be excited, but of course there's all of the modes at the horizon, and if order half of them are excited, that is again fiery drama. So this is an alternate. The assumptions sound a little bit different. There's no entanglement being used or throwing. There's no entanglement being used or anything, but it's probably the same argument, but it leads to the same conclusion that if you give me a random state in the Coulomb field theory in the part of the spectrum that looks like black holes, and you jump inside, you will find that many of the modes near the horizon are going to be excited. Now, I've made assumptions in this argument. So you'll remember that, you might remember, I went through it kind of fast. I mentioned several kinds of complementarity. There's what I call global complementarity. That was where there is one Hilbert space. Here the CFT Hilbert space. And the operators both behind the horizon and on and outside act in that global Hilbert space. This argument is posed in that framework of global complementarity. I'm assuming that this operator, the projection operator that acts on the modes that cross the horizon, I'm assuming here implicitly that projection operator has an image in the CFT when I say I can. Well, when I even write this operator down, I'm assuming that. So this you might evade with what I called strong complementarity. Where you have the Hilbert space outside, you have the Hilbert space of an infalling observer, and they have matching conditions. But again, the problem is they can both see this mode B that we're diagonalizing. And so it's not clear that strong complementarity, I think this argument still there's not such a well-developed framework for this idea, but it seems as though even this weakening of quantum mechanics doesn't evade this argument. And then there was what I called nonlinear complementarity, which we'll talk more about. In nonlinear complementarity, something like the projection operator onto whether the horizon modes are in their vacuum would not be a linear operator. Knowing its value, even if it vanishes on all of your basis. Okay, so if for a linear operator, if it vanishes on all your basis states, it vanishes on all states. But for a nonlinear operator, you can make up anything you want. It could vanish in your basis directions and be non-zero in all the others. And that's, of course, outside the framework of normal quantum mechanics. But one way to evade this argument is what I will call nonlinear complementarity, where, again, the observables behind the horizon are related to the observables outside by something outside the usual framework of linear quantum mechanics. Okay, so that's good. So that's all I have to say about fiery drama. So quantum drama. So let's imagine this thought experiment where we jump into the black hole. We extract this bit E from the early radiation, which is entangled with B. We captured that also, and we also have the bit B hat behind the horizon. And we have the choice of asking, are these two bits in the appropriate entangled state, or are these two bits in the appropriate entangled state? And there is no combined state of 3 bits that would have both properties. But suppose, in fact, that we could be talking about more than one Hawking mode. The infalling observer passes through many quantum modes, let's say dozens, hundreds. Suppose they do this 100 times, and sometimes they they look for this entanglement. These are non-commuting measurements, so we can't do both. But sometimes they look for this entanglement. Sometimes they look for this entanglement. And they always find the entanglement that's required. They find here the entanglement that would imply no drama. They imply here the entanglement that would imply information is conserved. Again, that would be like having a spin which, if you measure it in the z direction, is always spin up, and if you measure it in the x direction, is always in the x direction. So I'll describe a modification of quantum mechanics in which this happens. It's the final state hypothesis. So in cosmology, there was an initial singularity, and we're very happy with the idea that in fact quantum gravity provides, in place of that singularity, some unique initial state, like the Hartle-Hawking state. Why shouldn't, and this is Juan and Gary Horowitz, why shouldn't the same thing be true at a future singularity? So that there is some unique state that is imposed there. And I'll talk about what that means as we go along. But this predates the current discussion by 10 years. But this was an idea for how the information gets out of the black hole. And I'll draw it heuristically. Here's an early Hawking pair. This is B and B hat early. Here's a late Hawking pair. And the idea, roughly speaking, is that information kind of travels here, here, and here. It travels in some sense. Oh, sorry. Actually, well, the idea is that information in some sense travels forward in time, back in time, and gets out. Now, what does this mean operationally? Okay, so we have a system with a density matrix, and we want to ask a question. We want to ask, is some proposition C true? And so, the probability for that is that trace. Suppose the probability that we first see C and then D is this trace. We have to take our density matrix, put projection operators on both sides, and then our second projection. So this projects out the bit of the density matrix in which we definitely see C, and then this asks, do we consequently see D? And so this is the probability. This gives us the probability to find two successive measurements. Okay. So what's the rule here is that we calculate probabilities with the constraint that there is some final state here, and all of our measurements are conditional on this fixed final state. One thing that's nice about this is it kind of puts it seems like it puts the problem into the singularity, where string theory might come along and fix it. But it really is a modification of quantum theory to have this kind of rule. So here's the rule. Again, this is the state your system is in. This is a state which is provided by the dynamics of string theory. And this is how you calculate the probability for any outcome. And now you can get what you want, because the evolution gives you a smooth horizon. So your density matrix here has a smooth horizon, but your final state doesn't destroy information. And so what you have is, if you ask the question, are these in the proper state? You get the projection operator gives you 1 acting that way. If you ask, are these in the proper state? The projection operator gives you 1 acting that way. And so you can have 3 bits, and you have a theory of measurement which is not consistent with normal quantum mechanics for those 3 bits.
Don't you have to adjust the final state to get the right answer? So, in order to do the quantum computation that extracts E, you have to be both a very good experimentalist and a very good theorist, because you have to already know the unitary S matrix of the black hole, which means that you know what F is, and you've built it into your computation that extracts E. Yes?
So it's worth mentioning that not all forms of quantum drama are the same, because Juan earlier today described ER equals EPR, in which the act of extracting E from the early radiation excites the mode near the horizon. So this final state hypothesis is distinctly different from that version of ER equals EPR. And the reason is because the quantum
observer, don't you have to do a hell of a lot of work to find the unitary?
Yes, of course you do. The information problem always is required you to do a hell of a lot of work. Now it just requires you to do it fast as well, which is another question we could come to. But yeah, there's lots of questions here. I mean, you know, it's just, you know, there's disturbing issues with, obviously, with causality and even with unitarity here. And in fact, there's a recent paper by Pruskel and Lloyd which argues that the violations of causality even leak out of the, you can do experiments even outside the black hole that would, in which a later action affects an earlier measurement. So there's a lot of explaining to do if this is the way things work. But again, it's one of the ideas. Okay. Now, so there's kind of a slogan, or just more than that. There's a you know, there's a feeling, there's an idea in the wind which says that geometry comes from entanglement. Space-time geometry comes. It must be. There's something deep there, very obviously. But let me sort of implement this in the following way. And this is the idea that's known as state dependence, as worked out in most detail by Papadimos and Raju, also others like the Berlindes. But Papadimos and Raju's is the most thoroughly worked out. So here we have our black hole state. So we pick some pure state in the band of the spectrum that looks like black holes. And because of what I told you, if I pick out any mode, any Hawking mode, that mode looks thermal. And so we can expand in terms of so omega is the frequency of the mode, and then we have the mode B in its nth level, nth occupation number, times some state in the remaining, some normalized state in the remaining Hilbert space, B bar. And so the remaining Hilbert space, if we're talking about a big black hole in the de Sitter space, would pretty much all be inside the black hole. If we let that black hole evaporate, that remaining Hilbert space is you know, in the evaporation products. Okay, but now remember, general properties of chaotic quantum systems say that this is what a typical black hole state looks like. But if you'll remember, the A vacuum. So if we just focus, the A vacuum was a squeezed state. And in fact, it looks just like this. It's the sum e to the minus omega over 2t, n for b, n for b hat. So it seems as though there is a very natural identification here that we say, you know, that for any given state, we identify this with the so I'll write it this way. So we can pick out basically, we identify this as a state of definite occupation number for the inside Hawking mode, and then there's other variables in there that we won't go on and labeling. Now so now it seems as though we have a framework. This is very attractive. We have a framework in which typical states, thermal states,
are naturally identified as having vacuum near the horizon. I like this. Now, but how does it relate to what I said? Because I told you that we have a whole basis of states. We have a whole basis of states that don't have vacuum near the horizon, but typical states do. Something very nonlinear is happening here. Actually, I should say more about that, because I said, okay, I have a linear projection operator that asks the question, are the cross-horizon modes in their ground states? It's worth remembering that how quantum mechanics usually works. So if we think of gravity quantized canonically, we have some wave functional as a function of the metric and other fields. And if we want to ask a question, do I have a gravitational wave of such and such amplitude and shape? Do I have such and such matter excitations on top of my metric? All of those questions are asked by projection operators. A projection operator which picks out the piece of the wave function in which the metric has the desired form and in which the matter fields have the desired excitation. So, and this is a linear operator. So within our existing framework of quantum gravity, observables are linear operators. What's happening here is that the observable, so the reason that this can work is that the observables are not linear operators. In fact, these states here that I've identified in this way are really, I've overused them. As psi runs over the whole Hilbert space, the same state is given multiple interpretations. And so this is not as slick as it looks. It might be right, but it's only right in some nonlinear modification of what the observables are. A modification of the Born rule. Because if you don't have a linear projection operator, that means that you can have two states which are not orthogonal. Moreover, they can be actually, they have to be very, that you can have, there will be examples where they're very far from orthogonal mathematically, but where they're physically orthogonal. Where this one, you would say, is definitely in the ground state, and this one is definitely in the excited state. And then there's lots of questions. Quantum mechanics is weird, but what saves us from facing much of the weirdness is that it's linear. So, the reason that interpretations of quantum mechanics are something the reason we can just shut up and calculate is that quantum mechanics is linear. All the interpretations are the same. As soon as you give up linearity, you have a lot of things that you have to rethink and be precise about. And so if you're going to do this, there's a huge amount of infrastructure, of theory that needs to be rebuilt. You need so there are good. So there are you need. Suppose I superpose these two. Yeah.
Not in a general, but I mean let's assume that this is how we understand black hole.
Right. But then you need to be able to again. So let me call this state 1. You need to answer questions like, what is happening in this state? Also, when you start doing measurements and entangling with an apparatus. You need a theory of measurement. For every manipulation you might do to this state, you need a theory of what you will encounter on the inside. And it's very hard to make a consistent theory. One of the things I want to emphasize is, again, not all forms of fiery drama are the same. I mentioned how the final state version, of quantum drama, not all forms of quantum drama are the same. I mentioned how the final state proposal makes one prediction. And so you have a complete theory has to sort of be able to give an answer to any thought experiment. And we're kind of far from that. In fact, in the most complete implementation of this idea, it explicitly excludes a lot of questions. In fact, sort of all of the interesting questions that would really probe the theory. It also has the problem, it's very much based on equilibrium states. But once you have a black hole that's decaying and you manipulate its decay products, this very nice observation
doesn't really tell you how to proceed. So there's work. So again, there's much beauty in the idea that there's a relation between entanglement and space-time geometry. The question is how to implement it. Okay, so two more versions of quantum drama. So a lot of the thought experiments go away if you can't really extract the bit E. If the quantum computation is too hard to do on the time scale you have. Now, that doesn't save you from everything. The version in which the ADS version in which I had the basis doesn't use that at all. So this doesn't eliminate all problems, and it really raises more questions than it answers, because what it says is you're allowed to violate the rules of quantum mechanics as long as no quantum computer can catch you. How do you build a theory on that basis? Finally, ER equals EPR. So in one direction, the fact that quantum gravity on a two-sided black hole in the Hartle-Hawking state produces the thermal field state of the conformal field theories is simply true, and it's very beautiful, and it's clearly an important fact in this subject where we don't have enough sharp facts. The question is, does it also hold in the other direction? If we have this entangled state, do we necessarily have this geometry? Now, if we don't, what does it mean? If we don't, what it means is that, so this is the CFT, and this is the bulk. It means that in some sense there are degrees of freedom in the bulk that are not visible in the CFT. So in this not yet discovered bulk theory of quantum gravity, there are degrees of freedom which simply don't appear in the boundary conformal field theory. And that's not completely implausible, because if we have quantum gravity in a closed space, one still thinks you'd have non-trivial degrees of freedom even though there's no boundary. So it's not completely implausible that there are extra degrees of freedom here, and so this direction holds, but this direction is only holds when these additional degrees of freedom are in the appropriate state. That's one possibility, but then the other possibility, Juan has said this, and it's true with dualities, they tend to be maximally true. If something is true in this direction, it's true in this direction. And I just want to sort of, again, try to think of just a little bit. I'm not going to dwell on this. Think about the sense in which this modifies quantum mechanics. And Juan pretty much said it. He said, there's no projection operator onto entanglement. And maybe one way to, suppose I have three copies of the gauge theory, and this one has a black hole in it. And now I can imagine entangling it either with this one or with this one. So either this one is entangled with this, and this is in its own state, or this is entangled with this, and this is in its own state. So if this is entangled with this, then the with the two in this direction, if in this direction, again, the precursor construction gives us operators up here in terms of operators that act in both conformal field theories. Now, in this case, if these two are entangled, then the operators that measure what's happening behind the horizon are built out of these two CFTs. If these two are entangled, they're built out of these two CFTs. So they're different operators, and again, because there's no projector onto entanglement, as Juan showed, you can't in some way sort of promote these to linear operators with some kind of projection operator. This may not be the best way to explain it, but ER equals EPR in the strong sense, because it elevates entanglement to some, in the way it does takes you outside the linear framework of quantum mechanics. This may not be a bad thing. In fact, it seems to be a good, I mean, it would be exciting to learn something deep about quantum mechanics out of all of this, but it has to understand it's a modification in that way. Okay, so where is this going? And actually, I've been asked by, I'm fairly frequently asked by, especially by young people, what should I calculate? You know, there's you can look through this. I mean, well, the problem, of course, is we have too many calculations. Again, we have the CFT calculation, which says that pure goes to pure, and we have the bulk calculation that says pure goes to mix. So we kind of have too many calculations. We have to figure out what's wrong with one. But and you know, there's for example, with the stringy story, with the non-80-back stringy story, there are calculations to do. There's calculations to do, but you know, if we think back to the original sort of 20 years, the first 20 years of the information paradox, there was a very long period of scenarios and assumptions and challenging other people's assumptions. And then about 1996, people started calculating something. They started calculating what happens when you throw stuff at D-brains and what happens when you throw stuff at black brains. And they discovered interesting patterns. And after a couple of years of this, Juan put his finger on the pattern and said it's a duality. And so it may be that we're now in a similar phase, because when you look out there, there's a large number, especially of young people, who are either calculating entanglement entropies or, even better, are deriving general relations between entanglement entropies and space-time geometries. And I don't know where this is going. I mean, it's kind of orthogonal to my way of thinking. But if I just kind of look at this, the fact that so many young people are doing what looks like a very interesting body of work suggests that we may be in a similar phase. And what's waiting, so this is the calculation to do. But what you really need to do is you have to figure out what as Juan did with the brains, figure out what it actually means. And so maybe some of this will be useful. So I started with this equation. And now this is a classical equation in the canonical quantum theory. In the canonical quantum theory, this becomes an equation which I think Herman wrote down. The constraint equation, where H here is sort of just the operator version of this. And, you know, there's string theory, which has its equations. But if you think about this mantra, geometry comes from entanglement, you know, you're tempted to write down something like E stands for equations of motion. E of rho equals 0, where rho is the density matrix for the system. And again, the only thing I want to say is, again, at the level of quantum theory, this is a very different equation than this. This respects the linearity of quantum mechanics. This very much does not. So
what is E?
E is the equation of motion. I didn't have room to put it on the board, but it, yeah. It's like Feynman's U equals 0 as the equation. Yeah. So no, this needs to be filled in a little bit, but you know, but you know, this idea that geometry comes from entanglement suggests that this is the shape of the final equation, but this just doesn't seem right. I think, you know, much of the linear structure of quantum mechanics has to survive. There's this tension between the role of entanglement and the you know, and quantum mechanics. So this is the end of what I plan to say about black holes. I have half an hour, and I actually do have another. If you have a little, well, you've paid to be here, so I have time. I can pause for questions, and then I want to talk about something completely different, but it has connections with this school, and and I'd like to. It's a good thing to hear about. So any short questions about the lecture so far, other than what is E?
This last final stage has nothing to do with pre and post-election
Yes.
ideas.
Which
The thing, the final state.
is it different? I don't think it's different. I mean, maybe Juan would. Where's is he? It's yeah. I think it's similar. Yeah. Okay, I want to let you catch your breath. I'm going to actually start to write. I'm just going to start. This is a real change of subject, and but again, I think there's an interesting story I want to tell you. So, and it what you hit. So string theory has brains, and they have actions. So a p-dimensional brain has an action. The usual thing, determinant of the pullback of the metric and the pullback of whatever other fields and the world sheet action, and maybe the dilaton. And I want to ask what this action means, specifically the following. If I have a brain, and this action, then it will source the various bulk fields G and B and phi. So they'll be singular at the brain. So if the brain sources these bulk fields, if I now plug these bulk fields back into the brain action, there are divergences because the fields are blowing up as they approach their source. And the question is what to do with these. And this has bothered me for a long time, and it turns out to be necessary for understanding something very, very current. What most people do most of the time is they treat this in the probe approximation, where you basically don't insert the self fields. You just insert the background fields. That's sort of a formal expansion around the limit of having no brains in the system at all. But there's something which is better and more physical and more general, which is to regard this as an effective field theory. And in particular, then, the divergence, these purely classical divergences that you get, in fact, can be and should be treated by the usual framework of renormalization theory. And I wanted to mention this because Thibault, in his lectures about black holes, mentioned, several times, classical renormalization theory, and it's basically the same thing. And so I thought it was worth working this out. Again, especially because it has at least one interesting application. So to explain what I mean here, I want to take a simple model with less indices. So in the bulk, in the bulk, I'm just going to have a free scalar field. And for my brain action, I'm going to have, I'm going to let it, so it's a, okay, so it's a p-dimensional brain. And for simplicity, I'm just going to fix it rigidly. I'm not going to, fluctuations can be added in the same spirit, but I just want to, motivated by this issue, consider its interaction with some bulk field. And I've taken here an interaction which is simple but still interesting. So if I have my brain here, and I scatter a phi wave off of it, then because of the phi squared interaction, there's going to be some scattering amplitude. And all is good. But now, if you think about this as a Feynman graph, there's also going to be a second order interaction, like that. And now there's a divergence. So this is the fact that this is going beyond the probe approximation. This is the field produced by the brain, now evaluated back at the brain. Again, this is divergent. In fact, we can easily figure out the divergence because what we have here is an integral over the transverse momenta Okay, this is just a scalar propagator. And k parallel to the brane is conserved, so it's not integrate over, but k perpendicular, this is a delta function in position space, so we integrate in momentum space, and the dimension of the integral r is the codimension. It's d minus p minus 1. And you see that if r is 2, so we'll start, if r is 0, 1, we're fine. If r is 2, already there's a log divergence there. And it looks like a loop integral, even though we're doing a purely classical problem here, just solving classical wave equations with this action. And you do the same thing with it that you do in quantum field theory. And this principle has been rediscovered many times. I guess it was actually the subject of Thibault's PhD thesis. And it was rediscovered in the context of brane worlds by Goldberger and Wise. It's now sort of being rediscovered here. So, okay, what do you do? Well, you first of all cut off the integral. Well, you cut off the integral, but so you just put some upper limit on k perp. But what the divergence is telling you is that the physics that you see is sensitive to physics at much higher energies. This model doesn't know about the physics at higher energies, so what you have to do is you have to basically input a parameter from the high energy theory, and so you have to basically add in, called that G, you have to add in a counter term for that operator, which just has the role of providing the information about the high energy theory that you don't have here. So if we're talking about a D-brane, the high energy theory is string theory, and so what you would do in the first place is you would do a disk amplitude, and by requiring that this reproduce the disk amplitude, you would figure out what G is to this order. This is an annulus with two vertex operators, and so you would do the annulus graph, just enough of the annulus graph to extract the value of the coupling, and then from then on out, you could use the low energy effective field theory. Now, if this thing were instead a black hole or a neutron star, I guess this is Thibault's field, but again, you would match a theory of the internal structure of the object to the low energy physics, and in this way figure out what are the parameters in the low energy effective action. By the way, this, of course, when you see a log divergence, you know that there's another part to the story, which is as you go to lower and lower energy scales, there's a beta function. The effective value of G will run. So even though we're doing a purely classical problem, this theory actually has a beta function and a running coupling. Actually, you may have seen this before. Because what we're doing here is we're solving the field equation partial squared phi is delta of x perp phi. And this is basically okay, so in the orthogonal directions, the perpendicular directions where all the fun is, for r equals 2, this is basically the Schrodinger equation with a delta function potential. And you may have encountered that as a toy example of renormalization. And this shows you how that example kind of is embedded in a full quantum field theory. But actually, you can carry this to actually, before I go to larger values of r, of course you know that that when you get this action from a short distance effective theory, you have not only the leading term, you have all possible operators. And sometimes you care about the higher dimension operators. So we have that. And actually, we should do some dimensional analysis here. The dimensional analysis of phi, the units of phi squared
are mass to the d minus 2. So let me actually go to dimensionless. Kappa will be dimensionless. So these higher dimension operators are suppressed by more powers of the cutoff. This is this generalization of renormalization theory that was emphasized by Weinberg, where if you have a theory which is incomplete above some scale, and you want to study physics to accuracy of some inverse power of that scale, you keep not only the renormalizable terms, but you keep the non-renormalizable terms out to whatever dimension you're interested in. So now when we go to higher powers here, higher codimension, r equals 3, r equals 4, for D3 branes it would be r equals 6. The divergences get worse, and there are more divergences because there are subleading divergences that generate these operators. But it's just dimensional analysis. It all works out that whenever you find a divergence, it just represents something you don't know about the UV theory, and it always, the net powers of the cutoff from the integrals and the couplings are always such that what the UV theory does for you is it tells you what are the appropriate values of kappa of the couplings for the given cutoff. Okay, so this is sort of a, well, good. So this is just a review of sort of Weinberg's way of formulating effective field theory. And I think it's very useful because, again, it really tells you what the brane action is. It's not just something that's meaningful in the probe approximation. But now let me tell you why specifically I was interested in this now. And it has to do with the question, does string theory have de Sitter vacua? So if we think about ADS5 cross S5, if we dimensionally reduce on the 5 sphere and think about this as a 5-dimensional theory, there is a potential for the size of the 5 sphere, the modulus, the size of the 5 sphere, the potential for it. When that radius gets very small, there's a very big energy from the flux, which is getting squished. However, at larger radii, the dominant term comes, the positive curvature of the 5 sphere in the reduced theory gives you a negative term in the potential. So you have a positive term that dominates at small radii. You have a negative term that dominates at large radii. Both terms go to 0 as r goes to infinity, which makes sense because 10 flat dimensions are a solution to the field equations. And they produce a nice minimum here, and this minimum is the ADS5 cross S5 theory. And so here, this gives you a strategy for producing a de Sitter vacuum. And it's the one which has been the most useful so far. You complicate the solution. You add some additional flux or brane that provides a source of energy that gives you a potential like this. Again, it has to go to 0. Has to go to 0 at large radii. And so you need 3 terms. You kind of need a positive term that dominates at small radii, a positive term that dominates at large radii, and a negative term that dominates in the middle. It turns out that there's no way to do this for the familiar examples like ADS5 cross S5. There is no, the negative curvature term is very dominant. There is no term which is more dominant at large radii that would enable you to do this. And so the implementation of this came in the KKLT model, where I'm going to try to draw this. So what you have, that's a little bit of a cartoon, but the idea is that you have a positive flux energy, a negative instanton energy. The instanton energy turns off more rapidly at large radii, and so it's much easier to find some additional source of some additional form of energy density
that produces a near zero or positive cosmological constant. And the simplest version, the simplest form of this third energy is a D3 bar, anti-D3 branes. So this geometry naturally has 3 branes in it. Anti-D3 branes have the opposite supersymmetry. They're a positive energy density. But because supersymmetry is broken, when you break supersymmetry, there's lots of instabilities. There's always a potential instability to tunneling to infinite radii. But also, the ingredients that break supersymmetry can annihilate against the ingredients that are already there. So in particular, this D3 brane is sitting in a background field that has the opposite D3 brane charge. And it's diffuse. It's diffuse. That's the nature of the solution. But there should be some mechanism that allows them to annihilate. And the question is, how fast is it? And there's been a literature. So over the last 5 years suggesting that KKLT doesn't work. And therefore, it might be much harder to get de Sitter vacua in string theory. And it's based on the fact that when you study the interaction here of the brane with the background fields, it seems as though the fields, the induced fields, diverge at the brane in an unacceptable way. So it would be a graph that looks like this. Here's the brane, its field. Here's the background field. And there's this thing blows up as this approaches the brane. If we do this, it gives a divergent correction to the energy of the brane, which has been used to suggest an instability. Anyway, having heard the first part of this discussion, you will say this is something which will have divergences, and they should be renormalized, but all that they should do is to change the parameters within the low energy effective theory, nothing more than that, and that's all they can do. And so now the only degree of freedom in the low energy theory for the D3 brane is where it is. All it can do is move around and find a minimum of the potential, which is not a problem. There is no other degree of freedom for the D3 brane that would correspond to soaking up, in the low energy theory, that would correspond to soaking up background flux. And so this apparent divergence that suggested an instability was simply coming from the wrong way of thinking about the problem. And this point of view about D3, that the right way to describe a D3 brane is in terms of its action as an effective field theory, resolves this. So this is good. This is good. String theory does have seemingly de Sitter, metastable de Sitter vacua. To close,
The annihilation always has to be non-perturbative.
the annihilation is non-perturbative. Now, actually, so to close, there are 2 things I want to mention. Since kind of the theme of my lectures is the incompleteness of string theory, I want to point out that there are 2 places in this discussion where our current best formulations of string theory can't give us the answer. The first is here, where if this describes our vacuum, what is happening is we have several terms in the energy density, each of which is separately 10 to the 60th or 10 to the 120th times as large as their sum. There is a cancellation to one part in 10 to the 120th, and yet we do not, and if we knew what the theory, if we knew what string theory was, we would have some algorithm where if we knew what this state was, in principle, we could calculate this number. Our best current string technology can only give us the first digit, maybe even the 0th digit in this energy. So this is a place where our current understanding of string theory is just vastly short of what a complete theory should do. The other is, there is...
In this case, Joe,
Yes.
you're saying that for this calculation, it's more than a computational problem?
It's more, there is no formulation of string theory within which you could pose it.
There's no non-perturbative.
There's no you need a non-perturbative. Yeah, there's no non-perturbative formulation of string theory within which you can ask this question. And the other is there is a non-perturbative decay here. There's a known non-perturbative decay involving d5 branes wrapping the whole manifold. But there's another one where this flux kind of quantum tunnels until it's much, much denser near the d3 brane, and then they annihilate. So if you draw this kind of as a function of time, there's the d3 brane world volume. Time is increasing, and then it kind of dissolves into flux non-perturbatively. And there is strong evidence that this decay exists. In fact, it would be implausible if it didn't exist because there is no conserved quantity that would prevent it. And it's actually very similar to something else, which is the way a heterotic string, which was supposed to only be closed, can actually end in flux. And in both cases, we have no non-perturbative framework of string theory that can describe these decays. So just a reminder of that there is still work to be done. So thank you.